Introduction. The compounds obtained by the replacement of one or more hydrogen atoms of a hydrocarbon by a corresponding number of halogen atoms are known as halogen derivatives. These derivatives are subdivided as mono, di, trio, tetrahalogen derivatives according to the number of halogen atoms present in the molecule. In addition, the halogen derivatives may be further classified into different classes depending upon the nature of parent hydrocarbon. There are main two classes which may be further subdivided are given below. First is aliphatic halogen derivatives. Depending upon the nature of aliphatic hydrocarbon, they are further divided into three types. First is haloalkanes, second is haloalkenes, and third is haloalkynes. Second is halogen derivatives of aromatic hydrocarbons. These are halogen derivatives obtained by the replacement of one or more hydrogen atoms or aromatic hydrocarbons by halogen atoms. These may be subdivided as nuclear substituted derivatives, side chain substituted derivatives, etc. Now the alkyl halides or monohalogen derivatives of alkanes are the compounds obtained by the replacement of one hydrogen atom of alkane by a halogen atom. They have the general formula CnH12 plus 1 X or Rx, where X represents a halogen atoms and CnH2n plus 1 or R stand for an alkyl group. For example, methyl chloride, ethyl bromide and isopropyl iodide. Alkyl halides may be further subdivided as primary, secondary, tertiary halides according as the halogen is attached to primary, secondary or tertiary carbon atom. Now the nomenclature. First is common system. In this system, individual alkyl halides are named as halides of the particular alkyl group present in the molecule. For example, CH3Cl is named methyl chloride with CH2 is named as ethyl iodide and so on. Second is IUPAC system. According to this system, these compounds are named as given below. First is the longest straight chain of carbon atoms including the carbon which carries the halogen selected and the alkane corresponding to this chain is taken as the parent alkene. Second is the straight chain is numbered from the end which gives the smallest number of the carbon carrying the halogen. Third is the name of the halogen, chloro, bromo or iodo, and the side chain along with their points of attachment are added before the name of the parent alkane. Now the methods of preparation of haloalkanes. First is from alcohols. Alcohols are generally prepared by the replacement of hydroxy group of alcohol by a halogen atom. This can be done by using different halogenating reagent are given below. First is action of hydrogen halides. Alcohols are converted into haloalkanes by reaction with hydrogen halides under suitable conditions. Primary and secondary alkyl chlorides are obtained by passing HCl gas into corresponding alcohol in the presence of anhydrous zinc chloride. Gru's process. Tertiary alkyl halides can be obtained by reaction between tertiary alcohol and concentrated HCl even in the absence of anhydrous ZnCl2. Second is addition of hydrogen halide to alkenes. Addition of hydrogen halides to alkene yields alkyl halides. Third is halogenation of alkanes. Direct halogenation of alkanes under the influence of light results the formation of alkyl halides as like methane plus Cl2 in the presence of light yields to chloromethane plus HCl. Fourth is bihalide exchange, Finkelstein reaction. Alkyl iodides can be conventionally prepared by replacing the corresponding alkyl bromide or chloride with a solution of sodium iodide in acetone. Fifth is from silver salts of carboxylic acid. Alkyl chlorides and bromides can be prepared by the action of chlorine or bromine on the silver salt of certain carboxylic acid dissolved in carbon tetrachloride. Borodin Hans-Dicker reaction. In this, RCOAG plus Br2 in the presence of CCl4 yields to RBr plus CO2 plus AgBr. Here's the physical properties of haloalkanes. First is physical state. The lower alkyl halides such as methyl chloride, methyl bromide and ethyl chloride are colorless gases. Methyl iodide and majority of high members are colorless, pleasant smelling liquids. Members with very high molecular weights are solids. Alkyl iodides turns brown on standing due to their decomposition by light. Second is boiling point. In general, alkyl halides have considerably higher boiling point than the corresponding hydrocarbon. It is due to the fact that alkyl halides have higher molecular masses than corresponding alkanes. and are also polar in nature. Therefore, they have stronger intermolecular forces of attraction than the corresponding alkenes. Amongst the alkyl halides themselves, the boiling points may be noted. For a given alkyl group, the boiling point of haloalkanes follow the order of Ri greater than Rp or greater than Rcl. It is because the magnitude of intermolecular forces decreases with the decreasing size of halogen atom. Second is, for a given halogen, the boiling point of alkyl halides increases with increase in the size of alkyl group. This can be attributed to the increase in molecular size, which leads to the greater intermolecular interaction. For isomeric alkyl halides, the boiling point decreases with branching. It is because branching of the chain decreases the surface area, and consequently the intermolecular forces of attraction become weaker. Next is solubility. Even though they are polar in nature, alkyl halides are insoluble in water. This is because alkyl halide can neither form hydrogen bonds with water nor break the hydrogen bonds already existing between water molecules. They are, however, soluble in the organic solvents. Next is density. Alkyl chlorides are lighter than water, whereas bromide and iodides are heavier. The densities being in the order of Ri greater than Rp or greater than Rcl. With increasing size of the alkyl group, the densities goes on decreasing. And next is chemical properties. Alkyl halides are one of the most reactive class of organic compounds. They undergo a variety of synthetically important reactions involving nucleophilic substitution, elimination, reduction, and formation of Grignard reagents. Naturally, therefore, they are regarded as one of the most important synthetic reagents in organic chemistry. The important reactions of alkyl halides are discussed below. Nucleophilic substitution reactions. Alkyl halides contain sigma bond between sp3 hybridized carbon and a halogen atom. The halogen atom is more electronegative than the carbon atom attached to it. Therefore, the carbon halogen bond is partially polarized, the carbon acquiring small positive charge and the halogen getting some negative charge. The positively polarized carbon can be easily attacked by nucleophile reagents. When a alkyl halide is treated with a strong nucleophile reagent, the halogen atom is readily displaced as a halide in which a weak nucleophile as shown below. The alkyl halides undergo a number of reactions called nucleophilic substitution reaction, in which the halogen is displaced as halide ion by stronger nucleophile reagents given a large variety of products. The nucleophilic reagent may be a negatively charged ions such as OH negative, Cn negative, and O are generally added in the form of its sodium or potassium salt, or a neutral molecule having an atom with a lone pair of electrons such as NS3 and RNS2. The halogen atom which departs along with the bonding parts of electron is known as a leaving group. It may be seen that in the nucleophilic substitution reaction, the carbon-halogen bond undergoes heterolytic cleavage and the lone pair of electrons of the nucleophilic is used to form a new bond with carbon atom. Order of reactivity with respect to halogen. The strength of carbon-halogen bond is different alkyl halides, and therefore the reactivity of alkyl halide depend upon the nature of halogen atom. It is found that the carbon halogen bond strength follows the order CF greater than C, Cl greater than Cb or greater than C. The CF bond has the smallest bond length due to small size of fluorine, and therefore it has the maximum strength. As the bond length goes on decreasing with increase in the size of the halogen atom, bond strength goes on decreasing. Since Ci bond is least strong, it is broken most easily, so that the alkyl iodides are the most reactive and the reactivity decreases in the order Ri greater than Rb, greater than Rcl, greater than Rf. Order of reactivity with respect to different alkyl groups. For different alkyl halides containing the same halogen, the order of reactivity is largely determined by the exact mechanism of the reaction as discussed subsequently. First is replacement of halogen by hydroxyl group. Formation of alcohols when treated with aqueous solution of potassium hydroxide or sodium hydroxide or most silver oxide H2O, which furnish OH negative ions. Alkyl halides react with OH negative ions to form alcohol. Second is displacement of halogen by hydroxyl group. Formation of esters on treatment with sodium alkoxide. The alkyl halides react with alkoxide ions to form ethers. Third is replacement of halogen by cyano group. Formation of cyanide or nitriles when treated with alcoholic solution of potassium cyanide. Alkyl halides reacts with cyanide ions to furnish mainly cyanides or nitriles along with a small amount of isocyanides. Next is replacement of halogen by isocyanide group. Formation of isocyanides or isonitrides. Alkyl halides reacts with silver cyanide at high temperature to give isocyanides along with a small quantity of cyanides. Next is replacement of halogen by carboxylate group. Formation of esters when heated with silver salt of a carboxylic acid. Alkyl halides react with carboxylate ions to yield esters. Next is replacement of halogen by nitro group. Formation of nitroalkanes on heating with silver nitrate. Alkyl halides give mainly nitroalkanes along with a small amount of alkyl nitrile. Next is replacement of halogen by nitrite group. Formation of nitrides on reaction with alkyl halides with sodium or potassium nitrite. However, the main product is alkyl nitrite. Next is replacement of halogen by amino group. Formation of amines on being heated with an alcoholic solution of ammonia. Alkyl halides first change to primary amines. As the amine form is nucleophilic itself, it reacts further with the alkyl halide to yield ultimately a mixture of primary, secondary and tertiary amines and quaternary ammonium salts. The reaction is known as the Habermas ammonolysis reaction. Next is replacement of halogen by hydrosulfide group. Formation of thioalcohols when treated with potassium hydrosulfide. Alkyl halides react with hydrosulfide ion to form thioalcohols RSH. Next is replacement of halogen by mercaptide group. Formation of thioether when treated with sodium mercaptide. Alkyl halides react with mercaptide ion Rs negative and are converted into thioethers. Next is replacement of halogen by alkyl group. Formation of alkanes whose reaction with sodium in triether saturated alkyl halides change into alkanes. It is believed that sodium initially reacts with a molecule of alkyl halide to form an alkyl carbanion. This, being nucleophilic in character, reacts further with another molecule of alkyl halide to yield an alkane. Replacement of halogen by an alkyl group. Formation of alkynes when treated with sodium salt of alkynes. Alkyl halides react with alkyl ion to produce higher alkynes. Replacement by hyd groups derived from malonic ester or acetoacetic ester. Formation of substituted malonic ester and acetoacetic esters on reaction with carbon anions derived from malonic ester or acetoacetic ester added in the form of their sodium salt. Alkyl halides give rise to substituted malonic ester or substituted acetoacetic ester. Next is replacement of halogen by aryl group. Formation of alkyl benzene. Friedel-Crafts reaction on treatment with benzene and its homologous alkyl halides furnish alkyl benzenes. Other reactions: elimination reaction, dehydrohalogenation when treated with a base such as alcoholic solution of potassium hydroxide or soda amide. An alkyl halide undergoes elimination reaction by the loss of the halide ion together with hydrogen ion from an adjacent carbon. That's a beta hydrogen. The alkyl halide get hydrohalogenated on reaction with alcoholic potash or soda amide to form alkene. Next is reduction of alkyl halides on treatment with nascent hydrogen produced from a metal and an acid and or ordinary hydrogen in the presence of catalyst. Alkyl halides get reduced to form hydrocarbons. Reaction with active metals. Alkyl halides can react with active metal like lithium, sodium and magnesium to form different products. Next is isomerism on heating to about 573 or even low temperature in the presence of a Lewis acid such as anhydrous AlCl3. Alkyl halides undergo isomerism to form products in which the position of halogen is changed but carbon skeleton remains the same. We have learned about the alkyl halide undergo a variety of nucleophilic substitution reaction. It is interesting to know that, however, all the nucleophilic substitution reactions don't take place by the same mechanism. On the other hand, there are two different mechanisms possible for nucleophilic aliphatic substitution. These are biomolecular nucleophilic substitution reaction, abbreviated as SN2, and unimolecular nucleophilic substitution reaction, which is abbreviated as SN1 reaction. These are the factors influencing the occurrence of rates of SN2 reaction. They are: first is nature of alkyl groups in the alkyl halide. Second is the nature of halogen atoms in alkyl halides. Elimination of leaving group. Third one is nature of nucleophilic reagent. And the fourth is nature of a solvent. Here are the factors influencing the occurrence of and rates of SN1 reaction. There are nature of alkyl groups in alkyl halides, electronic factors. Next is nature of halogen atom in alkyl halides, ease of elimination of leaving group. Next is nature of nucleophilic reagent, and the last one is nature of the solvent. Here is a comparison between SN1 mechanism and SN2 mechanism. So first is SN1 mechanism. It follows first order kinetics and SN2 follows second order kinetics. Two-step reaction involving carbocation intermediates in this single-step reaction which occurs through our transition state. Third, the nucleophile can attack the carbon carrying the halogen both on the back and front side, although the back side attack predominates. The attack takes place exclusively from the back side. In case of optically active alkyl halide, partial racemization takes place. Complete inversion of configuration takes place. Reaction rate is determined mainly by electronic factors. Reaction rate is determined mainly by steric factors. Rearranged products can be formed. No rearrangement is possible. The order of reactivities of alkyl halides is tertiary greater than secondary, greater than primary, and greater than methyl halides. The order of reactivities of alkyl halides is methyl greater than primary, greater than secondary, and greater than tertiary. It is favored by mild nucleophiles, favored by strong nucleophiles, favored by low concentration of the nucleophiles. It is favored by the high concentration of nucleophiles, favored by solvents of high polarity, and SN2 is favored by solvents of low polarity. Thank you very much.